I've written what I think of as the basic electric field equations and electric force equations, where the electric field due to a point charge depends on a constant, depends on the charge, and depends on the distance. R here is the distance from the point charge. And this is just written for basically for the magnitude of the electric field. Because a point charge, the direction is something that you can just remember the electric field points away from a positive point charge. And the electric field due to a negative charge points toward that negative charge. And then the total electric field at some charge Q depends on the charge, tells you about the force on that charge. So if there's an electric field at charge Q, and I could even put, which I did up there, put vectors over these. The electric field at some charge has a magnitude and a direction. You multiply by the charge, that gives you the force on that charge at that location. You can put those two together and talk about the force by one point charge on another point charge, which is something, you put those two together and that's something that you can calculate. But I think most of what we'll do, and certainly my view of the quizzes will probably lead to this being a better way to think about it, that every point charge has an electric field that depends on 1 over the distance from it squared, and that every charge sitting in an electric field feels a force. So I'm going to leave you with this problem to work on. Problem 1 here is approximately 1/3 of a quiz. So I think this was probably a half-hour quiz, or maybe even longer, I don't know. But it had 3 problems, and you're going to see all 3 of them. But here's the first one. 2 charges, minus capital Q plus capital Q. Because they're equal and opposite, they make up a dipole. We can think of them as a dipole. So when it says an electric dipole is oriented along the x-axis, that's what they mean. They also mean the x-axis is horizontal. I'm not sure it says that. Test charge plus Q is placed to the right of this positive one at distance D. Calculate the magnitude and direction of the net force on the test charge. So I'll give you a few minutes to work on that and talk about that between yourselves. So let's talk about this one. I have a way I'm suggesting that you do this calculation. It doesn't have to be my way. Force by point charges on one point charge on another, you could use that, turns out, twice. But I'm going to suggest you use a different way. And that's, since the question is the magnitude of the force on this test charge plus Q, the way I'd like you to think about that is that the force on this test charge is just the charge itself times the electric field at that location. And the reason I'd like you to think about that is that I'd like you to think about how to find total electric field somewhere. And so this will force you to do that. To think about it this way, ask you to first find the electric field that's over here on the right on charge plus little q. By the way, little q and big Q, people use those all the time just to distinguish one charge from another. There's nothing special about capital Q or small letter q. They could easily have been called capital Q1, capital Q2, capital Q3, or small q1, small q2, small q3. They're just ways of identifying a charge. We do tend to use Q to talk about the magnitude of a charge, but capital letter and small letter don't mean anything. Don't mean anything special. So, how do you find the total electric field at plus Q. Plus Q is to the right of both of those others. Those other charges, the negative charge over here and the positive charge right here, are both to the left of this plus Q. So first, let's just do direction, and I'm going to ask you to tell me by pointing with your finger the direction of the electric field due to the positive charge plus capital Q, the positive half of the dipole, the direction of the electric field at the location of the test charge due to plus Q. So you can point right, up, left, down, however you want to, and I'm going to sit here until almost everyone is pointing one direction or another. So what direction do you say that it is? All right, everyone's pointing to the right. So plus capital Q, the positive charge. Electric field vectors point away from it. If I'm on the right, and away means toward the right. So if I'm over here, the electric field by plus Q is a vector over there. At the location of little q, the electric field's a vector due to the plus Q. I don't know how big it is. I mean, I don't know how big to draw it because I don't have units or size. But I do know how to calculate the electric field by plus Q. It's plus Q is a point charge. Plus capital Q is a point charge. So the electric field, the magnitude of it, I know it points to the right because it's a positive charge and I'm over here to the right, so it has to point that way, as all of you who pointed said, I think. But the magnitude, well, it's some constant K times the charge, which would be capital Q, constant K, capital Q, divided by the distance from the charge squared. What's the distance from the charge? D. So the length of that vector is given by that formula. So you know the direction because you know it's a positive charge. And if you're over here to the right of that positive charge, then the electric field vector has to point to the right, away from the charge. And you know the magnitude because you can use this formula to calculate it, and you know that the distance between the two is d. What about the negative charge? So first of all, when you're at location plus little q, in other words, the location of the test charge, point to the direction of the electric field, the direction the electric field at that location has due to the negative capital Q. So almost everyone pointing to the left, pointing in the other direction. To the left means toward the negative charge because electric fields due to a negative point charge, the electric field vector, wherever you are, is toward that negative charge. So if you're up here, it's toward the negative charge. If you're down here, it's toward the negative charge, E by negative Q, E by negative Q. Wherever you are in space around here, there's an electric field that points toward that negative charge. If you get closer to it, then that electric field will get bigger. And if you get farther from it, then that electric field will get smaller. But they'll always point toward negative Q. So points to the left, which means it's going to partially cancel the electric field due to the positive charge. How big is this? Is the electric field vector by negative Q over there at the right where the test charge is that can feel that electric field. And that points to the left. How big is it? Well, K. I just want to do magnitudes now. So I'm gonna take the magnitude of that. What's the distance to the test charge from negative Q? 2D. So 2D is what gets squared. Square the 2, you get 4, so that's 4D squared. And so E at Q, well, let's do the magnitude first. We have KQ over D squared to the right minus KQ over 4D squared, because that's to the left, so we have to subtract that to get the magnitude of the total. And so that's 3/4 KQ over D squared, and points to the right. Any questions about that, first of all? So the problem doesn't ask you about the force. The reason I was looking for the electric field at that location is that once I multiply that electric field times Q, the charge, I've got the force. The charge is positive. The electric field points to the right. F is QE. So F points right also. Because little q is a positive number. When I multiply it by a vector pointing to the right, I get a vector pointing to the right. The force points toward the right. Positive charges are pushed in the direction of the electric field that they're sitting in. Total electric field that they're sitting in. In this case, that total electric field is a vector pointing toward the right, so this positive test charge gets pushed to the right. If the test charge was negative, then it would get pushed opposite to the direction of the electric field that it sits in. So it would just be pushed in the opposite direction. Any questions on the end result there? Okay. Part 2, same quiz. Very large, thin pair of conducting plates are oriented as shown in cross-section. The plates are large like this. They stick out big this way and really big that way. Generally, I would say except that it's hard to do this on a quiz, I would draw them so they go way off the page. So you're not near any edges. And that's what you're expected to talk about here, is you're not near any edges. So the cross-section here is not, it's not all shown. This picture would be more like what you really see. And, oh, maybe I'd better finish this, because I think when I copied this and pasted it in here, I accidentally got rid of point B. Could be that point B was never there, and whoever gave this quiz had to tell everyone where point B was. But I think that these two plates like this, both of them positively charged, by the way. Point A is over there, point C is over here. And I'm going to put point B on the left. And the problem tells you that the total electric field at point A has a magnitude of 300 newtons per coulomb. Find the direction of the electric field at point A, the magnitude and direction at point B, and the magnitude and direction at point C. So knowing them, knowing the magnitude and direction is not the main thing, but being able to explain how you got whatever you got. So I'll let you all work on it for a few minutes. So on this actual quiz, you may have only had the amount of time I just gave you, unfortunately. I'm not sure how long whoever wrote this gave you all, but let's talk about it. So you have talked about in DL, you talked about charge being distributed on a plate, positive charge on a plate, and I'm not going to go through the discussion of this unless you really want to, but I think that the electric field lines, because the plate is positively charged everywhere and it's a gigantic plate, you know that the electric field to the right of the plate is going to be pointing to the right, points away from positive charge. To the left of the plate, it's going to be pointing to the left because it points away from positive charge. So the electric field lines are going to look like that. They're parallel to each other. Lines are just a way of trying to draw a picture that tells you about the electric field vector everywhere. Because to draw all of the vectors is, of course, to draw an infinite number of vectors, and that's just a mess. But the lines tell you a lot. The tangent to the line tells you the direction of the electric field. Because the electric field always points to the right, this has to be a line that's horizontal. So the line will always, so the tangent to it will always be to the right when you're over here on the right, or to the left when you're over here on the left. The density of electric fields, how close these lines are together, tells you about the strength of the electric field, about the magnitude of the electric field vector. Like if you're over here, here's how far apart the lines are. And when you compare that over here to really close, you find out the lines are the same distance apart. Far away, same distance apart as they are close together. Same density of lines. As you go farther and farther, because these lines are all parallel to each other, you can go as far as you want. The density of lines is the same, as long as this plate is very, very large. So as long as it runs way off the page, top and the bottom, then you know that the electric field lines have to be parallel to each other right here. And that means the electric field vector doesn't decrease as you move farther away. And so if you go to electric field vector picture, the electric field vector, when you're close and on the right, will point to the right, maybe look like that. When you're far away, it'll look the same. Same vector. Anywhere on this picture you draw the electric field vector, you get the same vector. And as you go farther away from the plate, it's still the same vector. To the left, really close to the plate, to this plate, points to the left because it's a positive charge plate, but it's the same length as all the others. If you're quite a bit farther from the plate, so the electric field vector, it's basically a uniform field. It's what's known as a uniform field. That means the magnitude and the direction are independent of location. So everywhere in here, on the left of the plate and to the right of the plate, everywhere in there, the electric field has the same magnitude and the direction is always pointed away from the plate. So that's what I think that you ended up with in discussion lab, is this idea that the electric field does not decrease as you move away from, I'll call it an infinite plate, or a plate that is extremely large where you're kind of near the center of it and not very far away. If the plate is only this big and you're this far away, then it stops looking like an infinite plate. You have to be close to the plate, or the plate has to be very big for it to be approximately an infinite plate like this. So, what about two plates? Well, over here on the right, the electric field, maybe I'll go back here. If I'm over here on the right, the right plate has an electric field that points away from it. The left plate has an electric field that points away from it. How about their magnitudes? I'm farther away from the left plate. Does that matter? No, it doesn't. It does matter what the charge is on those two plates, and this is not specified. I mean, if you look at it, they drew 5 plus charges here and 5 there, and so they're trying to tell you that there's the same plus charge on both plates. And that will always be the case. I've never seen anyone mess with you by putting different amounts of charge on the two plates. That would be an unusual situation, and I'm not going to do it either. So same charge on both plates, same electric field, doesn't depend on distance. So this electric field by the left plate is the same magnitude and the same direction as the electric field by the right plate. They both point to the right. So the total electric field at point A has to be to the right. You know the magnitude is 300 newtons per Kelvin. So what's the magnitude of the electric field over here at point A by the right plate? How big's what's the magnitude of the electric field by the right plate over here? 150, half the total. The right plate and the left plate have the same electric field. The two added together gives you 300 newtons per Kelvin, per Coulomb. And so the magnitude of each of them is 150 newtons per Coulomb. What about point B? Doesn't matter how far you are away from the plates. What's the direction? To the left by the right plate, to the left by the left plate, and the total is still to the left and has the same magnitude, 300 newtons per Kelvin for the total. Thank you. 300 newtons per Coulomb. My apologies to Coulomb. Although, Kelvin's no slouch. How about in the center? Electric field by the left plate, if you're at point C, what's the direction of it? To the right. Magnitude? Same as all the other vectors I've drawn. Doesn't matter how close or how far you are. It's an infinite plate, same electric field, independent of distance. This is electric field by the left plate. Direction of the electric field by the right plate? To the left. Because you're to the left of the plate on the right. Magnitude of those two? They're each 150 newtons per Coulomb. I got it right that time. And so they cancel each other. Total electric field in the center is 0 because you have a vector from each of them in the opposite directions of the same magnitude. So they cancel. Any questions about any of those steps in there? Okay, dipole, same quiz. Dipole is placed next to a positively charged, very large plate, as shown. The plate, of course, again, should be drawn much, much farther. Maybe I'll use a plate that I've used here and put this dipole there. Use superposition to draw electric field lines for the plate. I already drew those, but still, you can redraw them. Describe how and in what direction the dipole will move in response to the plate's electric field. So this is something that you're probably already going to assume about a dipole, but I want to make it clear. These two charges, the plus and the negative charge, are separated, and our model could be that they're separated by a stick. And the whole point is something is keeping those two charges apart. You could say, well, they're going to attract each other, and you're right. But something else is going on. That's in the real world, that something else is usually, if a molecule has a dipole moment, it's because quantum mechanics and these kinds of electric forces end up with producing a lowest energy state, which has a separation of charge. So it's a quantum mechanical effect that makes this negative charge and that positive charge fixed at a specific distance. And so the distance between those two isn't going to change. The question of motion is something you have to think about from 7b. Just to remind you, the net force tells you about the acceleration, and the net torque, I'm not sure you ever actually wrote it this way, but I'm going to write it this way, tells you about the angular acceleration, or the rate of change of the angular momentum. So torques tell you about rotational motion. Forces tell you about translational motion. Translational motion is when things fly through the air. Rotational motion is when they change their orientation. That's the two kinds of motion you can talk about, and you know how to talk about from 7b, and so that's what they're asking about. So I'll give you a few minutes to work on that one, and then we'll talk about that. All right, let's talk about this one. I mean, again, this feels like something that you've done in DL, so I don't want to spend too much time on it. If I went back to this kind of electric field line picture, I could say that the electric field lines tell you about the direction of the electric field at each of these locations. If I go down here, I see, well, electric field lines are pointing to the right, so the electric field points to the right. Up here, the electric field lines are pointing to the right, so the electric field vector points to the right at this location. How do I know they're equal in magnitude? Well, the density of these lines is the same everywhere. And so this is the same picture that I already drew here, that the electric field is the same at both of those locations. Now, what does that tell you about forces? Because talking about motion means figuring out the net force and figuring out the net torque. So forces, torques come from forces. So one way or another, we're going to have to figure out the forces. Let me get rid of these extra electric field vectors that I've drawn in various places and just worry about the two that are at the locations of the charges. If there's a positive charge on Q, is Q times the electric field at Q. This positive charge feels an electric field to the right, so this electric field points to the right. That's a positive charge, so that has a force to the right. Force on the plus charge is a vector pointing to the right. This negative charge at the bottom feels an electric field to the right. Same electric field. So it has an electric field vector pointing to the right, but the charge down here at the bottom is negative. And the negative of a vector is a force pointing to the left. So this feels the force on the negative charge points to the left. The electric fields are the same magnitude at the top and the bottom. The charge is the same magnitude, just opposite sign. So the forces are the same magnitude, just opposite direction. If they're the same magnitude and opposite direction, what does that tell you about the net force? On the total, on the dipole? One force one way, one force another way. Opposite direction, same magnitude. If you add those two force vectors together, 0. No net force, so no acceleration. So if you place that dipole there, it won't accelerate right or left or up or down. It'll just sit there. It's translational motion, which is what you get from this sum of the forces. It tells you about translational motion. Strictly speaking, it tells you about the translational motion of the center of mass. So some point about halfway in between those two charges. That point halfway in between doesn't go anywhere. The whole dipole doesn't go anywhere. It doesn't move up, doesn't move down, or left, or right. On the other hand, you pull to the right on the top, and you pull to the left on the bottom, and that's going to cause that dipole to rotate clockwise. There's a net torque clockwise, therefore clockwise motion. The orientation of the dipole changes. Because there's a clockwise torque, this dipole starts, it's just sitting there at the beginning. When you place it there, it starts to rotate. There's still a clockwise torque, so it rotates faster and faster and faster until it comes to a position like this. Once it's gotten horizontal, with the negative side toward the plate and the positive side away, it's been rotating faster and faster and faster. So when it gets horizontal, it's still moving. It's still rotating clockwise. And so it's going to keep rotating until it gets to the vertical position again, but now with the plus and minus switched. And then it's going to rotate. Then there'll be a counterclockwise torque. Actually, as soon as it gets past this equilibrium position, there's a counterclockwise torque that slows it down. It'll come all the way up to here with the minus at the top and the plus at the bottom before it stops. And what it's going to do is oscillate. And if there aren't any other atoms around, if there's no other way for it to lose energy, it'll just oscillate forever. In practice, there are ways of losing energy, and so it will slowly lose energy or quickly lose energy and eventually come to an equilibrium. And the equilibrium has the minus sign closer to the positively charged plate. So the equilibrium place that it would eventually get to has the minus sign close to the positively charged plate and the plus sign away. Is there a net force on the object at this equilibrium point? No, even though the minus sign is closer, the electric field at the minus sign and the electric field at the plus charge are the same. So the forces are equal and opposite still.